My name is Oskar van Rest, work for Oracle in product development and specifically focus on property graph technology. And this presentation is on the SQL PGQ Standard and its support in Oracle Database 23 AI. So this presentation has two parts. So the first part is focusing purely on the standard, which is actually similar to my talk at last LDBC TUC, but this time I will go through it a little faster in case it's new for people and it's going too fast. You could always rewatch the recording from last time. And then the second part is our set of news slides focusing on the SQL PGQ implementation in Oracle Database 23 AI. So first on the SQL Standard. So what is SQL Standard? I mean, it's a well-known database language standard developed by ISO, by a number of countries are involved, and it has 11 parts. So the first 3 parts, framework, foundation, schemata, those are like the foundation, like the basic SQL stuff, DDL, DML. And then there were 7 parts added to it over the years, with additional functionality. And the latest part is PGQ, which stands for Property Graph Query. So even though the SQL Standard came out in 1986, it has been there have been new versions coming out every few years. So the latest version came out in 2023, and roughly every 4 or 5 years, a new version comes out. So why integrate Property Graph with SQL? Well, a lot of data is already stored in relational databases, and essentially that same data can be used to create a property graph view over these tables. And in this way, all these existing data can be used in combination with property graph use cases, for example, to find shortest path. So SQL also has a lot of functionality already, such as group by, row pattern matching, window functions, and all those things can be used in combination with graph pattern matching to create a very powerful combination of features. And also the security model and transactional model, manageability metadata, all these things can be combined with property graph, and property graph can be integrated into them to create a solution without having to recreate all this functionality for property graph, because it already exists in relational databases. And of course, it allows you to join relational data or JSON data with property graph data within a single query. So SQL PGQ is the most recent part that has been added to the SQL Standard, part 16. 9075 is the standard number. And then, in SQL PGQ, property graphs are first-class database objects, just like views and tables are. And property graphs are view-like objects. So when you create a property graph, it doesn't actually copy the data from the underlying tables, but it's like a view on top of the underlying tables and views. And it's created using a create property graph statement that I'll show later. And then you can query it using the graph table, which is a new kind of like table expression inside the from class. So a from class can have one or more graph tables alongside other table expressions. So an example application is anti-money laundering. So let's say we have accounts, customers, account owners, and bank transfers, which are 4 tables. And then you can create a property graph AML on top. So here you see vertex tables and edge tables. So there's 2 vertex tables, accounts, customers. So those reference the existing underlying tables of the graph. And then we have owns and transfers, which are the edge tables. And then here you can define, for example, how edges relate to the vertices. So the source of the edge references an account in this case, and the destination reference an account. In case of the transfers, in case of the owner, so customer owns account, it doesn't specify the references because it's reusing underlying foreign key. to do this. And as you can see, for example, labels, customer, label, customer. If you don't specify a label, it will just default to the table name. So here we don't specify a label for transfers, so the label is going to be transfers. And then properties. There's also all kind of defaults. So if you don't explicitly specify the properties, like for the vertices, for this first vertex table, we don't. That means all the columns in the accounts table become properties. So defaults apply for labels and properties. You can have explicit labels and properties. So here we see two properties, when an amount. These are just some additional info. So you can have one or more labels per vertex table or per edge table. And labels can have any number of properties. And vertex and edges have keys, and edges have source and destination keys. And you can default to foreign keys if they exist. Otherwise, you can define those keys. So a sample graph. So here we see the graph table operator in the from clause. So it takes so you have a match where you specify your graph pattern, a where clause, which is can take arbitrary SQL value expression, and then a columns clause to project. Here in this case, we project four things out. And then in the outer select, you can reference. I mean, you could say select star if you just want to select all these four things, and here they are spelled out. Yeah, and it's called graph table because effectively it takes a graph as input, AML, and it produces a table as output. So, and then you get this result, which is just a table. Here are some details on the vertex pattern. So we have like variables and label expressions, and then a where clause. And for the edge patterns, again, the same, like a variable, label expression, and a where clause. And as you can see, you can omit all these things. If you never have to reference the edge, you never want to get a property out, then you don't have to give it a variable name. And then some more complicated, I mean, if you want to specify variable length patterns, then you can specify one of these quantifiers. So question mark means 0 or 1 iterations. For example, n, comma n means between n and m. And then here we have the unbounded quantifiers, which means they can iterate an infinite number of times. So star means 0 or more, as most of you know. And of course, these unbounded one, you have to be careful that you put some safeguards in place to make sure the query doesn't run forever. So here we see an example where we say starting from a customer C1 with customer ID 500 who owns this account. Now follow in between 1 to 4 transfer edges to another account of customer C2, and then we return some information of the customer C2. So this repeats 1 to 4 times. And this is a similar query. Now we introduce this as a variable T1, but because T1 essentially can bind to between 1 to 4 edges, so it's essentially like a list of edges. Therefore, you cannot directly reference T1 in the columns clause or in the where clause, but you have to put it inside a aggregation. So whenever there's a quantifier here, anything that is quantified has to be can only be referenced inside an aggregation. So here we count the number of hops, basically the length of the path, and then we do some group by here. And then for each of these lengths, we take the minimum length to get as a way to compute basically the shortest path. And of course, there's also shortest path built in. In that case, you can use the cleany star. I mean, cleany star cannot be used if you say keep all, because it could be infinite number of paths, but as long as you have some sort of way to restrict it using keep any shortest or another restrictor, then this is fine. And here we see the different path selectors you can choose from and the path restrictors, and you can use any of these in combination with any of these. So you can, for example, say keep shortest 10 acyclic path, which means give me the 10 shortest path, and they have to be acyclic, so they shouldn't have repeated vertices. All the vertices on the path should be unique. And then finally, we have this one row per vertex, one row per step in the SQL Standard, which allows you to get separate rows for each vertex or edge along the path. Instead of having only one row per match to your pattern, you can get multiple rows. And I won't get into details of this query, but essentially it can produce a table like this where you have 5 paths, and the first path, because it contained 2 edges, it's going to have 2 rows in the solution. And if we look at this result here, it was a path with 3 edges, so it's going to have 3 results in the solution. So this is kind of like unnesting your path data. So that was on the SQL PGQ standard. And the next couple slides are on SQL property graphs in Oracle Database 23AI. So we basically have implemented the SQL PGQ standard in Oracle Database. So 23AI stands for 23 is the year. It's like the most recent stable or database version of Oracle, and 23 stands for the year it came out, and AI because Oracle Database now has vector data type and vector similarity search and other AI capabilities. So creating a graph in Oracle Database 23AI is done using the SQL PGQ create property graph statement. And graphs can be created currently on top of tables, materialized views, and synonyms thereof. So not yet views, but that is expected sometime soon. And then, yeah, like in the standard, you can default to primary foreign keys, or you can explicitly define your vertex and edge keys. And vertex and edge tables can have multiple labels, any number of properties, and data type include all Oracle Database data types, including the new JSON and vector data types. And then properties can be arbitrary expressions. So it doesn't have to be a column directly. For example, here we create a property name that's based on the column's first name, last name, it's a concatenation thereof. And then we also have a zip, which is a field inside a JSON object. So more data is a column of JSON data type. And inside there we have an address, and inside there we have a zip code. And the zip code is a number. So zip is going to be Oracle number that you can query directly through your graph table. And you can grant others access to your graph using grant statement. Also, if underlying tables of your graph change, maybe some column got removed or something, or maybe the entire table disappears, then the graph becomes invalid. In some cases, you can simply recompile the property graph statement. In other cases, I mean, when actual like a table goes missing, you have to create or replace your property graph. And then there's also these new data dictionary views. So the metadata of property graphs, basically the schema of the property graphs is sits alongside other like SQL schema objects and it can be accessed through data dictionary views, which this slide shows. So here on the right, there's these bunch of new data dictionary views. So there's views for that contain the labels of vertices and edges and property names and keys, and this can all be accessed through SQL queries. For example, you can get all the labels of a graph named bank graph, and as you can see, the owner is sys, and then the label name, it has 4 labels: person, account, transfer, owner. So that was about creating property graphs. This is about querying property graphs using the standard graph table operator. So yeah, we support fixed length and variable length patterns using these quantifiers 1, 2, and as well as the aggregations. So here we see 2 count to simply give the path length, and a JSON array egg to aggregate the amounts into a JSON array amounts. And then in the where clauses inside graph table, you can use arbitrary SQL expressions, including simplified SQL JSON dot notation access, which is also a new feature that was added to the SQL 2023 standard. So here you can see, assuming like there was a column more data and that column is exposed directly as a property more data, then you can say like vertex P2 more data address line 1 string. And I'll show some more details on JSON in the next few slides. So the as of clause is an extension to SQL PGQ. It allows you to do this kind of flashback queries where you can say, query this graph, but not the most recent version, but query it as of this timestamp or this change number. So the SQL standard does not specify or leaves it up to the implementation to define exactly what the vertex net identifiers look like. It simply said that vertex net identifiers need to be suitable for equality operation and grouping operation, but the type is implementation defined. So in Oracle database, we are using JSON as a way to produce vertex IDs. So here we see a query where we get some IDs from edges, IDs. And this is what they look like. So it's a JSON object that contains some information, and especially by reusing the key value, the edge keys or vertex keys, this is a way to make these identifiers unique. And yeah, example use cases of vertex IDs is, for example, in visualization or exploration applications, you may want to visualize some vertices, and then later you want to query some more information about those vertices, and you can pass the vertex IDs into another query to get more information. So yeah, in the previous presentation, Alistair talked about property graph schema and how it relates to GQL, and also how JSON schema comes into play. So on this slide and the next few slides, I'm talking about schemas and how they relate to SQL PGQ, and also how JSON comes into play and JSON schema in Oracle's property graph solution. So first of all, is there a notion of a property graph schema in SQL PGQ? And not really, because there's no property graph schema object, or there's no statement that allows you to create a property graph schema. So instead, there are SQL schemas, or also called database schemas. And property graphs are objects in those schema, and there's other objects in those schemas, such as tables and views. So what exactly defines the shape of a property graph then? So create property graph creates the graph and defines its overall shape. What are the vertex and edge tables, and essentially the types. But also the existing definitions of underlying tables and views underneath the graph, they also essentially define the shape or the schema of the graph. And that those definitions consist of like column types, primary foreign keys, other constraints, even check constraints. For example, column value needs to be between 10 and 99. As well as in case of Oracle database, we also support JSON schema definitions. So for a JSON column, you can specify a schema definition that the JSON values need to adhere to. And then, so is there any support for schema flexibility? So I mean, graph definitions can be altered through DDL. So you can essentially change your graph schema. But that is, I mean, requires update to the data definition. If instead you want more flexibility, you can use SQL JSON and JSON schema in combination with property graph, which is what the next few slides show. So here we see a combination of property graph and JSON. So let's say we have this persons table with more data, column more data, which is of JSON data type. And then here we just have one example insert. So we, since this JSON, it doesn't have a schema attached to it, you can insert any sort of JSON values or objects. So here we have an address with address line, zip code, etc. And then you can create a property graph.
Oskar, excuse me. Just a few minutes left if you want to leave time for questions.
Okay, thanks. Yeah, almost done. So here we have, we create a property graph on top of that table. And since we use the more data directly as property, we're going to have a property more data. And then you can query it in your graph table using this JSON, SQL JSON dot notation syntax. So you can get the address line out, and then you get here, you get the values from here. You can add new types of data to a property graph. And again, yeah, with database schema changes, it requires you to do DDL statements. So you may want to alter a table of persons, add another column reachable. And then you also need to create or replace your property graph to add that new column as a property. And then you can now do an update query where you set that new property or column value to true. Whereas if you would use JSON, you don't have to do any sort of DDL. You can directly specify that you do this graph query where you find some persons, and then you set reachable to true inside that more data JSON object. And then this is the last slide. So this is just showing how JSON schema comes into play. So if you don't specify a JSON schema here, then this JSON can contain any data. Whereas if you add this validate, and then here's the JSON schema, then it means whenever you do an insert into this table, it's going to fail if it doesn't conform to this schema. So here in this bottom example, it's going to succeed for the first table, but it's going to fail for the second table because these two in red, they do not satisfy these constraints. These are just some references you can click on if you download the slides. So yeah, thank you. And please let me know if there are questions.